So I wanted to make this video to cover off the topic of PCIe operations on Intel-based motherboards, including how to do bifurcation and lane reversal when your BIOS probably doesn't even have the options. But to do this, we need to first explain what these two concepts are. Here is a layout of a standard consumer motherboard I have on hand with an old Intel 4th generation socket. The top port of this board is a PCIe X16 lane, but what does X16 actually mean? In the concept of PCIe, a single lane is a set of differential signaling pairs, one for the transmit side and one for the receive. In this particular model, we have PCIe generation 3, so a single lane with these 4 wires in total, 2 for each side, can do about 985 megabytes of data per second in a single X1 lane. However, this is generally not enough for most graphics cards. If you have profiled any system with NVTop or NVIDIA SMI, you will know that there is actually around 3 to 4 gigabytes per second of data being transferred when running something like a AAA game. Due to this, peripherals such as graphics cards do not generally use only a single lane, but rather a full X16 width, which using basic maths gives us around 15 gigabytes per second of data usable in the full link speed. If an X16 slot, like we show here, is only able to power X16 peripherals, the compatibility for devices will be a huge problem. Obviously, PCIe supports link negotiation between the host and the device to automatically select a link speed using the maximum amount of lanes supported by both sides. For example, a network card with only 4 lanes would be able to negotiate an X4 speed inserted into the X16 slot here. There are some caveats in this process. You cannot make a device with only 3 lanes or 5 lanes. And the supported lane counts are 1, 2, 4, 8, and 16 on most consumer systems. There is also 12 and 32 lane specs defined but never actually used in practice. On almost all consumer platforms, with the exception of maybe older AMD systems, the lanes are initialized from 0 to 15 as shown here. Generally, the lanes on the GPU do not fail, but failure does occur, and usually from human error. There are many cases of cryptocurrency miners inserting mining risers backwards into a motherboard, and this will kill the first PCIe lane of any graphics card. Many videos exist already of this issue, so I will not cover them here. When such a card is inserted into a normal motherboard, PCIe initialization does not work at all. This is because lane 0 on the GPU is dead, which means that none of the other lanes can start up, and the PCIe device cannot actually negotiate even an X1 connection. Usually measured with a multimeter and diode mode, you can get an open line reading or abnormal values compared to other lanes when you are probing the pins. There is often a brute force approach to solving this problem, provided the reference clock pins 1 and 2 on the backside of the board are still functional, and usually involves technicians rewiring PCIe traces or soldering wires onto a donor mining board in order to reroute lanes. Let's first explore why these trace rerouting actions actually work and what these technicians are actually doing when rerouting the lanes. Here is a close-up picture of a GTX 1070 board I have on hand. Each of 2 traces here forms a set of differential pairs for each PCIe lane. And you can see here on the board, these traces are actually visible, and each of these has a set of 2 that we can see clearly on the board. This allows the card to run in 1, 2, 4, 8, and 16 mode in conventional lane ordering. Now, suppose this card is dead, we will have a dead first lane here, which means that the card cannot initialize from the conventional ordering because lane 0 is used for all speeds and it cannot be used here. The majority of modern graphics cards support something called reversed lane initialization. That means that lane 0 can be swapped with lane 15. And when technicians are repairing the cards, usually what they will do is they will cut the traces here and they will take the lane 15 differential pairs on the front and the back, and they will rewire them to the front like so for the 2 traces. And I'm trying to draw this as best as I can. And they will cut the traces here so that lane 0 does not go to the physical fingers on the PCIe card. What this is essentially doing is forcing physically the reverse initialization of an X1 mode on the GPU. This is because when the GPU tries to initialize the rest of the lanes, because it's going from the reverse order, lane 14 is not actually connected to this physical location here, so that the card will only be able to run in X1. Here is a more detailed representation of how you would actually get something like an X4 speed going in a reverse lane order with this brute force approach. As you can see here, I've got the aqua lines representing rewired traces, and all of the yellow lines here indicate that we need to cut the traces physically going from the GPU core down to the PCIe gold fingers. And same on this side, we must cut the reverse end on 12, 13, 14, and 15 lanes. If a technician were to reroute 4 lanes from 15, 14, 13, and 12 to achieve X4 to lanes 0, 1, 2, and 3, they will also need to rework the backside of the PCB. The reference clock pins are also indicated here and should be measured to ensure that the PCIe interface is still somewhat functional, in addition to probing the remaining differential pairs with the multimeter in diode mode before attempting any sort of repair. For this particular card, the numbering for the capacitors for the differential pairs are 15, 14, 13, 12, 11, 10, 9, 8, and then 7 down to 0. And to reroute the traces, we would first need to do 15 down to lane 0, like so, and then 14 to lane 1, 13 to lane 2, and then 12 to lane 3. I've compiled a quick visual here to demonstrate some common configurations for lane reversal on the GPU side. Note that this is not just specific to rewiring for a trace repair, but it's also how the schema usually works for a lane reversal configuration for GPU PCIe initialization. Each highlighted region indicates an alternate scheme to initialize the GPU. It is possible in this case for repair to rewire either lane 15, 7, 3, or even 1 to the first lane, which is why you will see some guides also suggesting to simply rewire or change these 2 lanes around. For cryptocurrency mining, rewiring a single lane is usually sufficient to restore full performance to a graphics card, so doing more than 1 lane is usually not necessary. However, games require more bandwidth, and rerouting in GPU traces also poses the risk of signaling integrity, even if the card was somehow able to work. Instead of rerouting traces, we can instead turn to CPU configuration to configure the host instead of the attached device to run lane reversal, but this option is almost never available in the BIOS of a normal motherboard, including the one that I have currently shown before. However, Intel has public datasheets indicating hardware level configuration of the PCIe lanes on the platform, and we can use this to our advantage. So here I have the datasheet for the Intel Haswell 4th generation series of processors publicly available from Intel's own website. And we can see here that there are some configuration signals that we can use to send to the CPU in order to indicate different or alternate configuration mechanisms for each of the PCIe lanes on the device. Here we have CFG2, which is what we want, which says that PCIe Express Static 16 lane numbering reversal can be enabled if the config is set to 0, which means that we must pull this down to ground. However, the problem that we have now is how do we actually find this on each of our motherboards, and what needs to be done in order to enable this on boot up. On modern CPU generations, Intel usually releases a datasheet for each of the socket pinouts, and this will indicate the config pin locations located on the processor. I unfortunately couldn't find this information for LG1150, which is the model of my motherboard, but we do have an alternative. The platform is old enough that there are actually some board view files available of the socket. The model doesn't even need to match with our motherboard, we just need to know on the socket which pins map to the correct config register we need. On here, usually the config pins are located on the bank of resistors located here, and we can see here we have HCFG2, which we can then map to this pin here on the top end of the socket. Finding the CFG2 pin location of the motherboard is actually not that hard. All we need to know is we have the location of the actual CPU pin, which is this one here as shown on the board view, and we just use multimeter in continuity mode to check which pin it actually maps to. I've actually done that already, and on the top bank of resistors you can see here that it should go to this if I probe with multimeter correctly. Now that we have confirmed which pads on the motherboard actually map to CFG2 on the CPU pins, we can now pull this pin down to ground. Usually the best practice would be to solder a resistor onto the pads, but since this is a lab motherboard, I just added a small copper wire between CFG2 and ground in order to make this connection, as shown here. To demonstrate what this looks like on a real device, I placed some Kapton tape on the first PCIe lane pins on the graphics card to simulate a broken device. On boot up, the CPU and GPU will configure the top PCIe X16 lane in reverse numbering order, as shown by the Intel datasheet, and the GPU should be able to boot up. In the BIOS information page, you can see that the GPU runs in X12 speed and not the theoretical X8 limit. I think that this Asus board just has some issues with compatibility and with the PCIe power management. If we try to test this same graphics card in a normal X8 slot, it initializes from the first lane, which is now blocked, and monitor will never be able to obtain a signal from PCI Express graphics. This wraps up the content for this video, and as shown here, PCIe bifurcation is also possible to configure with the same config resistor overrides on the motherboard. If there is any interest in showing how this can be done on motherboards which do not support it explicitly as a BIOS option, then I may make another video, but it is generally the same method of modifying resistors shown here. Anyways, bye for now.